Hello everyone. Thank you for tuning into my presentation for the 2026 IEEE Symposium on Industrial Electronics and Application. My name is Samuel Hall, and today I'll be presenting my work titled Design and Implementation of a RISC-V based embedded vision system for face and motion detection. This work was completed under supervision of Dr. Tay Fei Xiang, Dr. Lisa Yong, and my industry supervisor, Mr. Daniel Cole. Embedded vision is being used for applications such as robotics, surveillance, and intelligent automation. However, recent research on RISC-V embedded vision has been largely focused on implementing deep learning algorithms such as object detection, tracking networks. And while these approaches provide high detection accuracy, they also require significant memory resources and dedicated hardware acceleration. In contrast, there has been relatively little research investigating whether lightweight classical computer vision algorithms can be implemented effectively on resource-constrained RISC-V soft-core processors. Hence, this motivates my work, which is to investigate whether classical algorithms, specifically the Haar cascade, face detection and Sobel-based motion detection, can be implemented within the limited memory and logic resources of the RT Spartan 7 FPGA, while still providing functional embedded vision capabilities. Here are some similar works that have been previous works that has demonstrated object detection using RISC-V processors. RISC-V has been adopted for embedded vision and object tracking applications. However, the general trend is to use YOLO or deep learning models for object detection. These approaches typically require dedicated hardware accelerators and higher memory resources. Here are some similar works where Haar cascade classifiers has been successfully implemented on FPGA platforms. However, most of these implementations are using ARM-based SoCs or high-performance FPGAs platforms, and the hardware acceleration enables high detection speed but increases the design complexity. Hence, this limited study that implements Haar cascade directly on lightweight RISC-V FPGA platforms. So from the literature, we can identify that there is a gap where few studies evaluate the classical vision algorithms such as Haar cascades and Sobel filtering on resource-constrained RISC-V soft cores, and existing studies generate and focus RISC-V with deep learning models or FPGA implementations of Haar classifiers using ARM-based platforms. So there is limited work investigating whether the lightweight classical vision algorithms can be feasible on a resource-constrained RISC-V soft-core processor. Therefore, this work has three objectives. First is to develop and implement a embedded vision system based on the NeoRV RISC-V processor using classical CV algorithms. Second is to implement servo control based on the detected object movement, and finally to evaluate the FPGA resources utilization and determine the feasibility of this architecture. Next, I'll be going through the algorithm. The algorithm can be broken down into three parts. First off is the Haar cascade, which is used to perform face detection using integral imaging and rectangular Haar features. Second is Sobel operator, which is used to compute horizontal and vertical gradients for edge extraction. And last and not least is the sum of absolute differences, which compares consecutive frames to estimate object movement. Together, these algorithms work to provide lightweight image processing suitable for embedded implementation. Here is the original methodology for my project. It illustrates the intended workflow of this project, which is first the OV7670 camera captures the images. The FPGA will buffer the image, or the Spartan S7 will buffer the image. The new RV32 processor, the RISC-V processor, will perform the image processing, and then finally it will output PMW signals to control two servo motors, pitch and yaw for object tracking. Here is the revised methodology for my project. During the implementation, the camera integration proved to be quite challenging due to the timing synchronization and FPGA resource constraint. Therefore, instead of using live camera frames, images were converted into COE files and preloaded into the BRAM. And this allows the image processing algorithms and overall architecture to be fully validated while leaving live camera integration as future work. Here is the system architecture, the final architecture. The new RV32 processor communicates with multiple BRAM modules through the XC Smart Connect. So separate BRAMs will store instruction, 2 image frames, integral image, and frame buffers. Custom servo controller IP is also connected through the XC4 Lite, which allows the processor to update servo positions through memory map registers. Here is the RISC-V processor that I use in the architecture. The communication core is the new RV32 soft core processor. It executes all the image processing algorithms written in bare metal C, and the XC4 Lite provides communication between the processor and the peripheral IPs. Here is the peripheral IP for my servo motors. A custom XC4 Lite peripheral was developed to generate the PWM signals. The processor writes the desired pulse width into the memory map registers. Then the hardware will generate a standard 20 millisecond PWM waveform to position the 2 servos. Here is my proposed peripheral IP for camera. Although it's not integrated into the final prototype, the proposed camera IP was successfully verified in simulation. It samples the OV7670 timing signals and stores incoming pixels into BRAM for processor access. Here is my graphic user interface, Python-based GUI, which is developed for system user interaction. The user can convert images into COE format. It can perform face detection and perform motion detection, and monitor the UART output in real time. This GUI is actually greatly simplified, greatly simplified for testing throughout the development. Here are some of the sample results you see from the GUI. There are several representative results. First, the HA classifier will correctly detect human faces while rejecting most non-facial objects, and some epsiloid objects can produce false positives because of their features resembling facial structures. Here is a motion detection result. The motion estimation was evaluated using 2 consecutive images. The software operator will extract the image gradient. Then the sum of absolute difference, the SAD, will then estimate the displacement between the 2 frames. Then the processor will calculate the horizontal and vertical movement, which is later converted into servo commands. Here is the detection result, the performance. So 20 images were used for preliminary evaluation. The system can achieve an approximate 70% face detection, 80% detection for ellipsoid objects, and 100% rejection for non-facial objects. So through this, the overall detection performance is approximately 83.33%. Since the data set is relatively small, I will treat this value and regard it as preliminary observation. Here are some of the challenges that I faced during the current prototype. First, the image processing algorithm is executed sequentially on the new RV32 processor. The HA cascade requires evaluating many sliding windows across the image, while the motion detection will perform repeated SAD calculations between the frames. Since these operations are software-based, they introduce a noticeably processing latency. Dedicated hardware accelerator will definitely significantly improve the performance. Next is the block RAM. So block RAM is a primary hardware constraint. So later on I'll show you the results, but most of the available VRAM is already utilized for storing the image buffers and classifier parameters. Hence, most of the images are loaded 128 by 128 pixels, and is loaded sequentially, so it actually limits the support for higher resolution images. Here is the example of the PWM equation. The detected pixel performance displacement is converted into PWM using this equation based on the OV7600 field of view FOV and the SG90 characteristics. Each pixel difference corresponds to a small angular movement, which is then translated into pulse width adjustments. This is done within a 50 centimeter range. Here's the example of the waveform. So these waveforms verify that the server IPs can correctly generate the PWM signals. The pulse width changes according to the values returned by the processor, which successfully confirms the communication between the software and the hardware through XC4 Here is the FPGA utilization report. So based on this, we can see through the table that the image, the design can comfortably fit within the RT Spartan 7 FPGA, and the main limitation is the DRAM. Approximately 91% of the available block RAM is occupied by image buffers and classified data, and this indicates that the memory rather than the computation is the primary constraint of this design. So what are the future works that I will want to do for this project? First off is to integrate the live OV7600 camera to compare the architecture on larger FPGA platforms like the RTX 7, the A7, and develop a dedicated hardware hard classifier, and lastly to expand memory using external DDR3. In conclusion, this work demonstrates that the classical computer vision algorithm can be implemented on a lightweight RISC-V FPGA platform. The new RV32 processor successfully executes speech detection, motion detection, and servo control within a memory map multi-VRAM architecture. Although the current prototype is using preloaded images instead of live streaming, it establishes that a practical foundation for future real-time embedded vision systems. And that is all from me. Thank you very much.